Hey everybody, welcome back to Environmental Studies 282. Today we're going to be talking about distributions and data. So this is our second lecture in our series. Reminder that these lectures are intended to basically be your homework. We're going to go over some of this material in class. In some cases, we might go over all of it in class, but for the most part, we're going to be trying to do programming or experimental design or a discussion of a paper or methods in class. So watching these before or shortly after class is going to be really, really important for you to get this information. So let's talk about distributions and data today. So the first thing we want to think about, and we've been talking about this a little bit already, is what is a distribution? What does one look like? And how do we describe it? We're going to go over this a little bit in class, but these slides are going to be a very comprehensive walkthrough of this concept. So as you can see, there are many different ways to describe data. Here we see all of these different kinds of distribution on the left. We have the uniform, the Bernoulli, the binomial, the Poisson, the geometric, the exponential, Weibull, beta, chi-squared, gamma, normal, or Gaussian, the log normal, and the student's t. There's a lot of different ways to describe data. These are all different examples of distributions. All of these distributions are showing us, let's say, a population on the x-axis, and then on the y-axis, it's just a count of the number of times we see a certain number within our numerical variable occur. So if we take a look at like this numerical, this uniform distribution here, we can see that we just have these little peaks, right? So every time we see a number, we get these little peaks, and it is these peaks that actually represent the data. So you can see that every one of the points is represented the same number of times. So that's it for a uniform distribution. For a Bernoulli, we see like only ones and zeros basically. And then we might be looking at some other different distributions that we're more familiar with, like the exponential distribution or the normal or the Gaussian distribution, where the mean is in the middle and then we kind of tail off to the sides, or the mean is over on one side and it tails off to one direction. So we're going to go through some of this a little bit more later in class. Just wanted you to get a sense for all of this. And then on the right of this is actually some data from a paper that I wrote in 2021. So you can see that I actually took the idea of distributions and applied it for a research practice. So here we're looking at basically the amount of recovery or resistance that corals have in different basins in the face of a stressor. So you can see that there are actually different distributions of how corals respond to things across basin. So we can use this concept to truly do science. Sort of underlies everything we think about when we think about a population. And we're going to get into that today. So before we start digging really deeply, we need to talk a little bit about the basics. These kind of variables that we're talking about, these numerical variables, we're really interested in pieces of them, and I'm going to kind of explain that a little bit more. But we're generally doing this thing called descriptive statistics. This is how we generally start when we're looking at a population or we're looking at experimental designs. We think when we have our data in our hand, the first thing we want to do is understand it and describe it. So we're going to want to look for, according to this little infographic, a measure of central tendency and a measure of variability. And those are a little bit strange. I'm going to change the words. When we're thinking about descriptive statistics and we're thinking about populations, we're thinking about science in general and data, we're really looking for a measure of the average or the center. So what is the mean response of a population? What's the center of the distribution? And the spread. So if you remember one thing about this lecture, it's like we're really, really keen on comparing center and spread. Those two things are essential for all of the statistics that we're going to learn in this class and for all of the basics of experimental design and of understanding data in science. So when we say the center, we're thinking of the mean, the mode, and the median. And those are all slightly different. The mean is the average, the mode is the most common number, and the median is across the entire distribution. This is the number that's exactly in the middle. They all explain something about the center of the data. If we have a perfectly normal distribution, like a Gaussian or that normal curve, all of these numbers will be exactly the same. Anytime we skew away from perfectly normal, they might move around a little bit. So when you're thinking about your data, it's important to understand your distribution and to think about which of these variables you want. Usually we want the mean in our work. The second thing we have to care about when we're thinking about a population, we can't just compare means, we have to compare means and also look at the spread of the data. And I'll give you lots of examples of why over the course of this semester. So the spread of the data might include, again, the range, the mode, the standard deviation, some measure of the spread. Because really, the analysis of variance, the t-test, the kind of statistics that we're looking at when we're comparing, does one population differ from another population? We need not just the mean, but we also need to understand the error term or the range of the data. If the data overlap too much, even if the means look different, the statistics might tell us that we don't have enough power to determine the difference between those two things. So that's really what we're trying to focus on here. Note that all of this that I just talked about is for numerical data. When we're using categorical data and we want to understand the difference between one and another, we actually have to use a portion or the fraction of observations in any given category instead of like the number, the mean. Okay, let's take a look at another graph that shows us a bunch of different distributions. These are mostly just here so you can see them because people will use a lot of different names to explain a lot of different distributions. And here's just an example. I'm just putting this here so you have it. I'm just going to carry on right through it, but there are a lot of different kinds of distributions. We usually think about the following. We can keep it pretty simple. Most of the time we think about the bell curve or the normal distribution. And this is straight out of the textbook, Whitlock and Schluter, which is roughly the basis of the statistical concepts we talk about in this class. So you can see we have a uniform distribution at the left, and then we have a bell curve or a normal distribution there, second from the left. And you can also see how the bell curve might change where it shifts towards one side where the mean is a little bit more to the right, or if we could even have a bimodal distribution where within a population we have like one mean and then there's kind of a small group that has a second other mean. So if we have a bimodal distribution, a lot of our assumptions about statistics, which assume a normal distribution, are really untrue, right? Like if I calculate just one mean from a bimodal distribution, that mean is going to appear like, if we calculate a grand mean of all the values, it's going to appear like right there. And that is not representative of the actual response of that population. So in that case, the mean is really not what we want, or we need to figure out how to change or break this distribution up. We might even modify it with a standardization principle. So we really want to be thinking about our distribution first thing. So one of the first things we often do when we start looking at data is we just make a histogram. That's what all of these are called. These graphs are called histograms. So the normal distribution or the bell curve, like I just said, it's assumed to be the distribution of basically all data in the biological and environmental sciences. Not always true. It's very much not always true. We can think of this in a lot of different ways. So do you think that the assumption is logical in biological and ecological data sets? And I'm telling you that it is the assumption that we make. And in a lot of cases, the answer is that it's not super logical, but there are ways we can make it fit better. The number one thing we think about is we could always have more samples. If we take more samples, we increase our sample size, we'll have sufficiently large N to assume normality. And if we take enough samples, we're basically going to get a normal distribution. So I'll show you that in a little bit. So we've been talking about the idea of distributions, and now we're going to apply this to sampling distributions. How do we take the right amount of samples, and how do we build distributions that are what we want? So just a reminder, we basically never look at the entire population of interest because it's usually too big, right? I think we gave an example last time of, let's say you're on the quad at Bates and you really want to understand what the average growth rate of the grass is. You can go out and measure every single blade of grass in, I don't know, right when you get to campus in the fall. And then like right at the end of fall, you can go back as we start getting into cold weather, the leaves start falling, and measure the height of every single piece of grass again. And the difference between the two tells you the growth rate. But we just can't. We're never going to have enough time to measure every single blade of grass. So instead, we might go with a quadrat and we might sample like 100 blades of grass, like, 30 times, something like that. Especially if we have like all of us in class, if we all go measure 100 blades of grass once, and then we all go measure 100 blades of grass again, we actually might get a real value. So that's, what we would do. So that's how we take a sample of our population, and that's why we do it. And remember, the population will have a certain distribution, and so will our sample. And it is possible that the distribution within our sample and the distribution within our population will not be the same. So we hope to infer the true population parameters from our sample using the concept of estimation. This basically means we're trying to take a representative sample of our population. Our ability to do this depends on how representative our sample is, and due to chance, it may not match the population exactly. So we need to think about that. If we only take one sample and it's not representative, we are totally wrong about everything we're thinking. So that's problematic. How do we deal with this? We take more samples. So here is an example of the probability distribution on the y-axis and the sample mean and distribution. If we take 20 samples at the top, so if we take 20 samples, we get this pretty wide distribution, and we still get the mean that looks about like everybody else's mean. If we take 100 samples, we'll see that our distribution gets tighter, right? And then if we take 500 samples, even tighter. We have a really, really, really good idea of what the true mean is, and we have very little variance. This accuracy and precision is what we're after. We can't always take 500 samples, but maybe 10 isn't enough, maybe 20 isn't enough. We need to get to a place where we have a really good probability density. If you want to explore this concept on your own, you can do that with this activity that I'm going to open up for you real quick, hopefully. Cool. This is from the Whitlock and Schluter book. This is an example of how you can sample populations. So over here on the left, you can set your sample size. N equals your sample size. I'm going to just start with a sample size of 5 because that'll be fine. And then you can change your population level mean to, let's say 120 is the population level mean of the fish length in millimeters. And sigma here is the distribution, or sorry, is the standard deviation. So we can just make it 25. So these are the population level parameters. And now we're going to sample and see how representative our samples are. So we can choose one sample, one individual. That one individual, our mean is 120, and that one individual is 160. So that's not representative. Take another one, 96. Again, not the mean. 132. It's closer to the mean. Let's take 5. This is our distribution if we only take an N of 5. Here's our population level distribution. That is not great. Our sampling distribution looks like this. So now, if we calculate the mean of that sample, there's our mean. And then we can take another sample of 5. Again, not great. Drop the mean down. Again, not great. Right? And we're taking our samples of 5. So let's just take a bunch of samples of 5 and calculate a bunch of means. You can see that we still actually get relatively close to the true mean. So even if we're taking small samples, if we take lots of them, we're still going to get pretty close. Now, let me just try to reset all of this, see if I can. Yeah, okay, cool. Let me take 100 samples of 100. Here's a sample of 100. It gives me basically the exact distribution of the full population. That's awesome. Now, let me take many, many, many samples of 100. Look how tight that gets. Really, really good. So lots of big samples is the key. But we had to balance our time, energy, resources, and what's possible for us. So hopefully that was useful for you. There is a link in the PowerPoint where you can explore this a little bit more on your own. All right. So to define the sampling distribution, what we've been talking about, it's the probability distribution of all values for an estimate that we might obtain when we sample a population. This represents the population of values for an estimate and is not the real population. This is the values within our sampling, like our sample size, the distribution of our sample, not the distribution of the population. They are different, right? We're hoping that it represents the population, but it is in fact just the distribution of the sample. All right. A little bit of moving on to our next concept here, describing data. So we're thinking a little bit about spread and variance. So here is an example that I built in R. It's pretty straightforward. We can make it ourselves here, and we might even do that in class. We're thinking about the idea of spread and variance. The histogram on the left displays, well, let's define histograms first. Histograms show us the frequency of an observation on the Y, or the count, the number of times that observation occurs, and a variable on the X. The variable must be numerical. And we can see the shape of the distribution. We can also see the spread. So we can get a general idea of like what shape of our distribution we have. Is it normal? Is it something else? And we can also see the spread of our data. How wide is our error? In this case, we have a data set called penguins, and they're measuring the length of the bill in millimeters of 3 different species of penguin. And what you can see on the left is that we have sort of this weird amorphous blob that's like roughly normally distributed, but the bin sizes are pretty big and it's not super clear what's going on. One thing you can't see on the left is that there's actually 3 different species of penguin within this distribution. So if we break it down with the 3 different species and colors, you can kind of see that the species like maybe look a little bit different from one another. And this is just a preliminary data visualization. So it gives us a sense that maybe we want to do some statistical tests to see, is there a difference between the bill lengths in these populations across these species? Is there an effective species on bill length? Seems like there might be. So, we're thinking now about the spread and the variance, but what else do we want to see when we're describing data? We've talked about this already. We want to see some measure of the center, the sample mean, the median, or the mode. We've already defined them. They're defined here just so you can see them. Here's our histogram again. I've thrown in the mean, I've thrown in the median, and we're not a perfectly normal distribution. So we have to figure out what the mode is. And remember that the mode is the value that occurs most often. And if we look at our sample, we can see that we have 2 spots where we have the most often occurring thing. So maybe our distribution isn't quite perfect and maybe we're not quite normal. But also histograms, if I can get this to pop up. Histograms are based on the concept of using bins. So they're not ideal for reviewing centering stats, especially the mode. So that's basically like there's 5 different numbers that are within this bin here. So this bin is pretty wide. You can see on the x-axis, it encompasses about, I think, 5 millimeters. So anything that's within this 5 millimeter range gets put into this bar. So looking at mode and looking at centering stats is not great in a histogram. It's kind of our intro to graphs. There are other things we might look at instead. We might get a nice smooth line function instead, for example. So let's take a look. What can we do? I guess I should get rid of that. What can we do instead of using histograms? We can visualize centers and spread using a box plot, which shows us the black line in the middle is the median. It's very important to remember that it's not the mean. In R, the default for every box plot is that it shows you the median with a black line. Okay, we also see this thing called the interquartile range, or the IQR, and that's what's in colors here. The IQR is the middle 50% of the data. So it's quantile 2 and quantile 3, which basically are the quantiles just below and just above the mean value. So then you also see these lines. These lines are essentially the first quantile and the 4th quantile, so the lowest 25% of the values and the highest 25% of the values. And basically, they just show you a measure of the spread. They go out to the furthest point away from the middle of the data that isn't an outlier. An outlier is not included in this distribution and is excluded by showing itself as a dot. You can change it to an X or something else if you want, but outliers are excluded from this kind of visualization. So box plots are great because they're really simple. It's 1 line of code and they show you a measure of the center and the spread, and they also throw some outliers out there. So they're doing a lot for us. And here we're again looking at bill length by species, and we can see that we do have this Adelie, this one penguin species that seems to have a smaller bill length. You also see that the population distributions, they do overlap some, right? Everybody's inside here someplace. So maybe there isn't difference here, and maybe there is. One thing we can't see is how frequent any of the occurrences are. So if we really wanted to see that, we could be super extra and do a violin plot. The violin plot is called the violin plot because it looks like a violin, allegedly. You could also call it an ink blot plot or whatever you want, a Rorschach plot. I don't know. You can choose your own adventure there, but this is called a violin plot. Here we can see the histogram of the data turned sideways. So we can get a sense for where the most common values are in the distribution. And we can also see some interesting stuff, like this is bimodal. And this is roughly bimodal. And this is maybe bimodal, but there's just a really big median range. Now, I'm curious if you can think of a biological reason why that might happen. Why would we have a distribution when we're looking at the whole species we're looking at 3 different species of penguins, and each of these distributions is a little funky and possibly bimodal? It is possible that there's a sex effect here, right? Where biological males may have a different size bill than than biological females. That's something we can look at a little bit in class, maybe. Let's explore that. All right. I can even show you how this might work. What we're looking at in this plot is not a box plot, but is instead, we have calculated the mean, which are these bigger dots, and they're kind of hard to see. This isn't a perfect graph, which is part of the point. There's a big dot right here, and there's a big dot right here. And the blue big dots indicate the biological sex is male, and the pinky red indicate female. And in case you were wondering, those are default colors. I didn't like choose to illustrate the binary in such a way. They just are default colors in R. Okay, so we can see that we have some difference between the blues and the reds, right? So we have our populations, we have our raw data plotted in the background, which is really nice. We get the center and the spread. We can see how each of our populations of penguin compare to one another. And then we can also see that there generally is an effect where the male penguins have bigger bills than the female penguins. With some exceptions, of course, like there's this one female penguin up here that is just like the biggiest, which is cool. There's also a few penguins where they could not tell you who was who. Penguins are actually not super into the binary. But also it can be really hard to sex a penguin because they flop around a lot. And if you hold them, they bite you. I can ask me about that sometime. Been bit by a penguin on a couple of occasions. So that's a great way to visualize center and spread. We have our box plot. We might even try our violin plot, and then we'll move on to what I think is a little bit better way to do it, which is looking at the raw data in the background and the mean and the error bars in the foreground. We are going to learn how to do this in our graphing section of class. It's promise it's not that hard or scary. Okay. So we talked about center and spread. We should also talk about how we define variance. How would you define spread or variance of data, and what does spread look like? Most people will come up with this one. Most people will say, well, let's look at the standard deviation. We should learn like what that is and how that works. And we're going to, if not today, soon. So let me show you some stuff. All right, what we see here is what we've already been looking at a lot, which is our bill length across our different species. And here I've plotted every single point that you see in each of these distributions, each of these populations. Haven't divided it by sex. This is just all the penguins. You can see all the raw data. This is our spread. It's a visual of variance. It's maybe not the most informative visualization of variance, but it is one. All right. We might think about these other metrics of variation when we're defining variation and thinking about how we want to show it. The interquartile range, which we've already seen, the standard deviation, the standard error, and something called a confidence interval, all of which are slightly different. We are in the next couple of classes and over the course of the semester going to understand and play with all of these a little bit. So don't worry if it's all new terminology. There's no test on it. We are just going to work through it. Let's define them all right now. Here comes the math. I'm putting it all on a slide so that you can see it. I don't usually like to make slides with this much text, but I want you to have something to refer to. And we don't really have a textbook per se. So this is that for you. Here you go. The interquartile range, which we've already talked about, is the span of the middle half of the data from the first quartile to the third. So that's this bit of the data right here. That was supposed to be one of those fancy arrow thingies. Hopefully you know what I'm talking about. I'm not great at drawing, but that box is the bottom of the second quartile to the top of the third quartile. That's the interquartile range. All right. The IQR is often shown with the median of a data set in a box plot. We've already talked about that. This is the median right here. The median is the exact middle point of the data, and the math on the median is that it is, as you see it there. You take your observations and you divide it. Basically, you divide it by the sample size. Okay. IQR can be calculated through first calculating the first and then the third quartiles. A quartile contains 25% of the data. So the first quartile is the first 25% of observations. The second is 25 to 50%. You get it. Okay, we've already talked about all of this stuff. So I just wanted you to see. Here's the math on how to calculate a quartile if you're interested. To calculate a quartile, you identify which quartile you want to calculate. Let's say we want to calculate the first quartile. We will then, hello? multiply the ending percentage of that quartile by 0.25, or sorry, of that quartile, which is 0.25 by the sample size n. So if we have the sample size of 16, and we know that the quartile that we're looking for is the first one, we multiply by 0.25, and that equals 4. So that tells us that the first 4 observations are our first quartile. So we're looking again at the data here at the bottom. Quartile 1 is going through 0 through 4. Quartile 2 would be the next 4, and then the median, and then the next 4, and then the third quartile, and then the next 4. If the calculated value is an integer, then the first quartile is the average of our number of observations. In other words, the first quartile is the average of observations 4 and 5, is the average of observations 4 and 5 below, which is 2.34. So the quartile will end. It tells us the number of I'm doing a poor job at explaining this, but it's telling us the number of integers that'll be inside of our quartile. But it's also telling us that the average of 4 and 5, which is 2.31 and 2.37, that the quartile is the average of those two, and that's 2.34. So we would draw the line where the quartile starts at 2.34. Hopefully that makes sense. Where I'm using some weird terminology, y sub j, as we've seen it before, y sub I is the ith observation, y sub j is the observation of interest, which is in this case the fourth. So y sub j plus 1, that would be 4, and 4 plus 1, which is 5. Hopefully that makes sense. If not, check out the Whitlock and Schluter section, but we also don't need to worry about that fancy notation. If j is not an integer, which is our value of interest, so in this case it came out to be 4, you replace it with the next integer that exceeds it, so you round it up. Thus, the first quartile equals y sub j. Okay, so let's calculate the third quartile using this logic. So if we take our n of 16 and we multiply by 0.75, 16 times 0.75, we get 12. So that means we should go over 1, 2, 3, 4, sorry. We get 12 as our quartile. So that's going to be here, right? So our third quartile, which would be the end of our interquartile range, would be the average of 3 plus 3.09 divided by 2. So that's 3.045. 3.045 is our third quartile. Hey, look at that. Third quartile, 3 plus 3.09 divided by 2 equals 3.045. So we did it. That's the interquartile range for you. If you want to calculate the interquartile range, sorry, I didn't tell you that. If you want to calculate the interquartile range, it's just the difference between the start of the first quartile and the end of the third quartile. So the third is 3.045. The first is 2.34. If you subtract, you get 7.05. So if you take your median and you add half of 7.05 to each side, you get your interquartile range. Roughly. Pretty cool. Okay. A box plot again does this for you automatically. You don't have to do any math. The box plot just makes it. So here's your box plot and a visualization of the interquartile range. Interquartile range is really great. It can be used quantitatively to delineate something called extreme or outlier values. Such values are defined as any value that is 1.5 times the interquartile range that we just calculated above the interquartile range. So our interquartile range is 7.05. So if you are 1.5 times 7.05 above this third quartile, you're an outlier. So that's why this here is an outlier. So if you are 7.05 times 1.5 above this line, like this one is, you're an outlier. That's how you calculate that. Again, the box plot in R does this for you. And I will show you some code where you can get outlier calculations on your own. To calculate an extreme outlier, which is like really, really different from the distribution, instead of using 1.5 times IQR, you use 3. Some people think that removing outliers is bad. There's not like a right answer here. I'm curious what you all think. You can think about this. Is it really bad? Is it really good? Here's an example of why it's really bad. If you are a person, say like me, who's really, really interested in how organisms respond to climate change, sometimes it's really, really helpful to keep the outliers in, because if I have an organism, let's say a coral, and I'm measuring bleaching percentage, pace of bleaching, something like that. And I have one coral that just like won't do that. It doesn't bleach. You subject it to temperature stress over and over again out in the wild. You're doing surveys, everybody's bleached, but this coral is just like not me. Do I remove that from my data set, or do I instead basically focus my research on understanding why are you like this? Me as a physiologist, what I want to know is why things are like how they are. Why did you survive? What is allowing you? What's the mechanism that is allowing you to be there doing that response? So for me, outliers are interesting. But it's also possible that I'm in the research lab and I'm streaking a whole bunch of plates with a bacteria. I don't know what bacteria. I'm not really a microbiologist, but let's say I'm growing bacteria in the lab over a bunch of different mediums and testing the effect of heat or something on all these different growths. And one time, instead of like streaking the bacteria that is my bacteria, I contaminate my sample. I like sneeze onto it or something, and that plate just goes totally all over the place. Like there's growth everywhere. It looks really gross. And you're like, wow, I put that plate in the coldest condition, knowing that heat would make the growth go faster. And then I had all this ridiculous growth. Yeah, that's totally real. I should totally keep that. But I can recognize that I maybe made a mistake, right? I can look at that plate and say, like, you probably need to be excluded from the data set. I don't even need to do an outlier test, but if I did, you'd probably be one, right? So some reasons why you might exclude and some reasons why you might keep outliers. And we can talk about this more in class if people have questions. So that's the interquartile range, one measure of spread. Now we need to talk about standard deviation. Standard deviation indicates the difference from the mean. It's calculated as the square root of something called the variance. The standard deviation is symbolized as S, and the variance is S squared. Deviation is the difference between a measurement and the mean. So what you're doing is you're taking your measurement and you're subtracting it from the mean. And you're doing the absolute value of that, right? Okay, what I'm showing you in this graph here is the mean and the standard deviation of bill length in penguins by sex and species. So that's the mean response of each sex and their bill length by species, right? We've got our mean here and here, and our deviation bars here and here. So the mean is the center, the deviation is some measure of spread. It is showing us the difference from the mean within the population. Okay. The variance is not the mean of all of the individual deviations in a population. That value is generally 0 if we have a normal distribution. Instead, we have to average the squared deviations. And if you like math, here's a formula for you. S squared is the sum of all of the differences from all of the samples minus the total mean squared over the sample size minus 1. We use minus 1 for a reason. I'll get into that in a minute. So the summation of the squares of the variance in the numerator is called the sum of squares. This matters for statistics. I'm just introducing you to the concept. There again is no test. You're not going to be doing this by hand. That's not nice. This is just how it works. We use n-1 in the denominator here because it gives us a more accurate estimation of population level variance than using n. So that's why we use n-1. It's very common to do that. So here's a bunch of observations in a population. We're calculating our deviations from the mean, knowing the actual mean. And then we square those deviations to give us these other values, these S squareds, which we're then going to be using to calculate the variance. So the variance is the S squared divided by, or sorry, is the sum of squares, which is this value. Sorry, I'm not using my, should be using this. We calculate all these different values, the sum of squares, and we end up with this sum of squares value 0.735. So that goes into the formula over here. We divide by n-1, which is a total observation number of 8 here. Minus 1 is 7. So 0.735 divided by 7 is 0.11. That's our S squared. And then we're going to do the square root of that to get our standard deviation, which is 0.324. So you can see then that our standard deviation in that past graph comes from that kind of calculation. We would calculate all the S's, then we calculate all the S squareds, we'd square root that, and that would give us our standard deviation, which is going to be 0.324. I know that that's a lot, but that's how standard deviation works. And now you know. We're going to talk about it a little bit more. Standard deviation is very useful in understanding the spread of data. And here is kind of why that is. If we happen to have a normal distribution, 67% of the data will fall within one standard deviation of the mean. 95.5% of the data will fall within two standard deviations of the mean. These are the data in the population, not necessarily how the mean will respond. This is all the data in the population. So two standard deviations of the mean, and we have a normal distribution, 95% of the data are going to fall in there. We can be 95% confident that the data, the values in our population are within that area. Okay, standard deviation measures the variance in the population. It doesn't measure the variance of the mean. For that, you need something slightly different, and that is called the standard error, or the standard error of the mean. The standard error of an estimate is the standard deviation of the estimate's sampling distribution. It reflects the precision of an estimate. It shows the differences between an estimate and a target. And we often consider the standard error of the mean, which is the standard deviation divided by the square root of the sample size, as a better way to look at variance, to tell whether there's truly a difference in a mean between populations. The higher the sample size, the lower the standard error. Let's unpack it just a little bit. Where did it go? Killing it. Okay. There is a formula. You can kind of see the standard error over here. This is the formula. It's a little grainy. This is representative of the standard error of the mean. So sigma y, it's a sigma, is the standard. This is the standard deviation or the standard error formula. So standard deviation of the mean. I'm just making a mess. Let me just point instead of making all these lines. Standard deviation of the mean is equal to the standard deviation of the population divided by the square root of the sample size. We can call standard deviation of the mean the standard error, or the standard error of the mean. When we do this math, we end up getting this graph. So we've got our bill length for penguins plus or minus one standard error of the mean for all the variables. So you can now see there's clear separation here and here and here and between this and all of those, right? So this is what I like to call a visual hypothesis test. If I were to say, I think that there's an effect of species and sex on mean bill length, or that there isn't, I could test that with statistics, but I could also look with my eyes, which are more powerful than math usually, and say, do I see trends? I'm looking at my means, and I'm trying to understand if my means and the variance of those means differ from one another. And I can look here and I can say, yeah, they probably do. Generally speaking, males of all three species look like they have bigger bills than the females of those species. And generally speaking, the Adelie penguins look like they have the smallest bills relative to the chin straps and the gentoos. Now, is there a difference between chin strap and gentoo? I probably need my stats to tell me that. But if the error bars don't overlap, I might be able to say that, yes, there is in fact a difference. It's not 100% sure that that's going to work out, but that's how I would interpret this. So it's really, really useful to be able to build a graph that contains the standard error and the mean. Confidence intervals even better, which is what we're going to talk about shortly. So how do these error bars compare with standard deviation? Here's how they compare. This is your standard deviation on the left, where we're looking at the variance in the populations, and there's lots and lots of overlap. And here on the right is the mean with the standard error. So you can see that we have this like huge shrinking as we go from standard deviation to standard error. And again, we're looking at the mean and the population level variance with the standard deviation. And on the right, we're looking at the mean and then basically the variance within the mean. So we can be pretty confident that the mean lies between those two bars. And if that's the case, we can have like a visual of whether or not there is a difference in the overall mean responses of these populations. Okay, again, to reiterate, for a normal distribution, we can be 67% sure that a single data point lies within these error bars, one standard deviation or one standard deviation of the mean. We read it like this. I can be 67% sure that any data point in my population of male, biologically male penguins of the Adelie species lies within this error bar. I can be 67% sure that any value within my population lies in there, versus I can be 67% sure that the mean response lies within these error bars, right? So I'm pretty sure there's a mean in here. I'm pretty sure there's a point, any point in here. So standard deviation and standard error have different reasons to be on your graph. So points in our sample lie within these bounds. That shows some level of variance in our data. That's the standard deviation. That is not best practice for how you graph when we're thinking about stats. So just so you know, like we probably won't be plotting a lot of standard deviations in this class. Okay, on the right, we get an error term for our mean value. The mean likely lies within these bounds. We're 67% sure. That shows the variance of a parameter, a mean, and not of our data. And that is a little bit more preferable for how we do hypothesis testing, which we're going to learn later in class. So we like to plot standard deviation or standard error instead of standard deviation. So just remember that. The standard error is the standard deviation divided by the square root of the sample size. Okay, and now we have to move on to our last measure of spread, and that's the confidence interval. And it's going to take us a long time to understand how to do this. We may not get there this semester, but at least you'll have seen the concept. A confidence interval is a range of values surrounding the estimate, for example, the mean, that is likely to contain that population parameter, maybe the mean, for example. The most common confidence interval that we think about is a 95% confidence interval, which basically translates to this. When we look at a 95% confidence interval, we can be 95% certain that the true mean lies within those two bars. That's really powerful. That's like very literally the statistical test that we're trying to run. So here's an example. 20 researchers took independent random samples of 100 genes from the human genome. Each calculates an average and a 95% confidence interval. There might be some variance due to chance. True mean of the population is in yellow. How many samples do not contain the mean? When we look at this, what we'll see is the mean and the 95% confidence interval, meaning if we see that this yellow line lies within our distribution, it's in our population, or it's in our sample. There's only one that doesn't do a great job, and it's that one. 95% confidence interval does not overlap with the yellow line. So this one is definitely different from the true mean. If you're really interested in the math here, check out Whitlock and Schluter, but here's the answer to your question here. They did 20 of these, 19 divided by 20, that's 95%. 95% of these samples contained the true mean. We were 95% confident that it would work out, and it did exactly as we thought. So that's pretty neat. If you want to calculate a confidence interval, there's a quick way to do it. If you have a perfectly normal distribution, 95% confidence interval can be calculated as 2 times the standard error. That's the 95% confidence interval of the mean. 2 times SE equals an approximation of 95% confidence interval if we have normally distributed data, and only if. We're going to learn how to calculate this maybe later in the course when we talk about the t-test. We might do that. It might not happen. If you want to see how confidence intervals are calculated, there's a nice little app here. We can take repeated samples of, let's say, 50. Repeated samples. Wow, we took a bunch of samples. Here we go. We're taking all of our samples. The true mean is 105. That's this value in black here, this line. We're taking a bunch of samples. So far, does it line up with the true mean? Let me see if I can pause this. We've had 152 samples and only 8 have failed. We're basically floating right around 95% in our ability to get this right. So if you want to play around with the parameters and understand how it might change a little bit, you can, but that's just showing you how sampling works. I'm gonna pause. You can also change it to a 99% confidence interval, and we'll do even better. So feel free to play around with that. All right. Now, I just want to show you a comparison of all these error terms, and this is sort of how we're going to wrap. This is not just sort of, this is how we're going to wrap today's lecture. On the left, from Whitlock and Schluter, we have gene length and nucleotides. That doesn't matter what that means, but we're looking at the mean gene length, basically. Here's our raw data in red. You can see that the distribution is quite big, right? We have our mean plus 1 standard error here. We can be 67% confident roughly that our mean lies there. 2 standard errors, we can be roughly 95% confident that our mean lies within those values. It's almost exactly the same here as this 95% confidence interval. And then we also have the standard deviation, which again shows more of a variance in the overall sample and not in the mean. So we're not comparing to anything, but you can see that this just breaks down very differently. Okay, on the right is a graph that I made that in hindsight looks kind of terrible, but here is how you think about it. You have your mean, and I'll show you in the chin straps because it's got the easiest ones to look at. Your mean are the big dots. There's our pink mean and our blue mean. Clear my stuff. So we're looking at the difference between this blue and this pink. Okay, and in black, this is our 95% confidence interval, which is 2 times our standard error. Inside of the black, you see the blue, which is our 1 standard error. And then outside of that, you get your pink, which is this bigger one here. And that's the standard deviation. So the standard deviation of these two even overlap. And they overlap or almost overlap in all cases. In fact, they do overlap in all cases. Here's one and another. Here's one and another. So you can see the standard deviations of these two when we're looking at within a species, when we're looking at the biological sexes, they do interact. They overlap the standard deviations. But the standard errors, they don't overlap. And the 2 standard errors, they definitely don't overlap. And when you do stats on this, you're going to find that there actually is, for all 3 species, a difference statistically between the male and the female penguins. So better to show standard error or 95% confidence interval than standard deviation when we're doing a statistical hypothesis test. And I know that we're jumping the gun on that. We're going to talk about hypothesis testing, I promise, but I just wanted you to see how this works. So this is how we think about data and distributions and why it matters. I know that that was kind of long, but hopefully really informative. Probably way more time than we're going to have time for in class. So this will be here as a resource for you. Please don't forget that we're trying to watch these when they come out so that we can get ready for our next class, and we're building towards working on more R in class and for more discussion as well. So thanks for your attention, and I'll see you next time.